Hi there. In this video, I'm going to give a conceptual overview of inner product spaces, orthogonality, the Gram-Schmidt process, and Hilbert spaces. So each of these concepts follow from one another. So I'm going to start with inner product spaces. So when we talk about inner product spaces, we're actually referring to a special type of vector space that have a certain type of operation, and that operation is the inner product. And when we speak about the inner product, we're speaking about the dot product. So the characteristic of inner product spaces is that these vectors have this dot product associated with it. And the purpose of the inner product is to ensure that we are able to measure the length of the vector or the magnitude, and also to give us an idea about the angles between different kinds of vectors, which then leads to the concept of orthogonality. And inner product spaces, they are generalized for higher dimensions. In fact, this is the purpose of defining an inner product space to begin with, and we'll see what this means just now in this video. So we can consider what we already know, and what we already know and are familiar with is the xy plane. This is the usual 2D space that people perform many calculations. And if we have two vectors in 2D space with x and y coordinates, they are vectors A and B. So this 2D plane is an example of an inner product space, and all of the calculations that we've been performing have been part of this framework. So the general characteristics of inner products is what we know about dot products in general. So if we have A dot B, and each of these vectors have coordinates A1, A2, and then B1, B2. So let's just say that A is equal to 1, 2, and B is equal to 3, 4. Then the dot product would be 1, 2 times 3, 4. And this would just be 1 times 3, which is 3, plus 2 times 4, which is 8, and that gives us 11. So another characteristic of inner product spaces is that when we take the inner product of a vector with itself, we actually get the magnitude. So if we think about A dot A, what we're actually saying is that we are taking the square root of A dot A. So it's, 1 squared plus 2 squared. So this would be equivalent to the theorem of Pythagoras, and that gives us the square root of 5. So this is all that we know very well, and that all with what we are familiar with regards to dot products. So just one other thing to mention here is the fact that we speak about projections. So the whole purpose of thinking about the dot product is to talk about projections. So a projection is essentially asking the question, how much of a certain vector, for example B, is in another direction. So the projection of B on A is asking how much of B is in the direction of A. So the magnitude of B in this direction is what the magnitude is. So when we take the dot product, A dot B, we're asking how much of A is in the direction of B, or how similar are A and B. If B was in the direction of A, they would essentially be 100% similar. So the magnitude of A in this dot product remains the same. And then the question was how much of B, or what proportion or what percentage is in A, and the percentage of B that's in the direction of A depends on the angle between A and B. So the percentage of B that's in A is actually the magnitude of B multiplied by cos of this angle. So the magnitude of A remains as is, and then we're multiplying it by B cos theta, and B cos theta is the proportion of B that is in the direction of A. So the dot product is actually looking at how similar are these two vectors in terms of each other. So if B was in the direction of A, theta would essentially be equal to 0, and cos of 0 is 1. So that would just be the magnitude of A times the magnitude of B. So cos of the angle is the correction that allows to put B on top of A. So that's what we mean by projection. And also in the broader scheme of things, projection is asking how similar is one vector to the other. So that also means we can actually calculate the angle between the vectors. And if we just solve for cos theta, then we can see that A dot B divided by the magnitude of A times the magnitude of B tells us what this angle is. So at this point, you're probably thinking, this is all fairly obvious, right? I mean, this is what people have been studying for ages, and this is all that we know. So what is the point of saying that this is an inner product space? What is the context of this? Why would we now define something that we already know as an inner product space? Well, the answer to that is the fact that we're thinking here about positions. We're thinking in the XY plane and all of that. What happens now if we extend this to higher dimensions? For example, 4D space or 5D space, maybe even infinite dimension space. What meaning does it have to take the magnitude of a vector? If we can take as an example, let's just say rainfall. So we have rainfall, the likelihood of rainfall in a given day. And let's just say that this depends on a variety of different vectors. Perhaps it depends on the temperature. Maybe it depends on atmospheric pressure. Perhaps humidity. And also something like, wind speed. So if we take this information about the weather and we put it inside a vector, we have a 4D space. We are now working in 4D space. So we need to be able to think about this vector. We need to be thinking about what is the magnitude of this vector. Perhaps we can think about the magnitude of this vector R as being, the probability or likelihood of rainfall being on a certain day. So the fact that we take the magnitude of this vector, or the magnitude of this vector is essentially equal to R dot R, the only reason why we are able to do this is because this vector R exists in an inner product space. So we specifically define an inner product space as being a vector space in which, when we take the vector R and multiply it by itself like this, or take the inner product, then we get the magnitude. This property is only possible because we have defined R as specifically existing inside a vector space. So that is a key point to note here. And that's the whole point of inner product spaces. So it only exists with these properties because we define it as an inner product space to begin with. So in order for R to have any meaning, that's the magnitude R, then we have to specify it in this particular manner. We can also think about projections and what meaning they have. If we think about now R1, perhaps now this vector has all this information that on a certain day, let's just say day 1, we measure all of these things and we put this in a vector. Then we go on another day and we measure vector R2. So if we're asking how similar is R1 to R2, then we're also thinking about the inner product, and that will tell us the extent of the similarity in a certain context. So that projection is also an important property of inner product spaces. So the next concept in this video is that of orthogonality. So we say that two vectors are orthogonal or perpendicular if the angle is 90 degrees. So as an illustration of this, then we can just have, a vector, and then we have an orthogonal vector. And if the angle between them is 90 degrees, then they are orthogonal. So this would happen if the one vector with the dot product of the other vector is equal to 0. So essentially we're asking ourselves what is similar between the vectors, and the answer is that nothing. So remember that dot product tells you how similar the vectors are, and the fact that it's equal to 0 means that they have actually nothing in common. So that's what orthogonality means. In other words, they are independent. So if the vectors are completely independent, What this means is that we can simplify a lot of our calculations, because since they are independent, it means that we can analyze each of the vectors independently and they don't interfere with each other. So that helps the calculations quite a bit. And everywhere in physics and engineering, if we have forces and motion and whatnot, what we would usually do is that we would split these vectors into different components, orthogonal components specifically, maybe in x and y directions and so on, and then we would perform calculations with each of these different uh, components independently, such that we are able to analyze the system more easier. So if we have two vectors, u that's equal to 1 0, and then if we have v equal to 0 1, then the dot product of this vector is going to be u dot v, and that's going to equal to 1 times 0 plus 0 times 1, which is equal to 0. So what this means is that this two vectors forms the basis of the 2D plane, and we can actually write any vector in the 2D plane as a combination of two of these vectors. So the next part of this video is that of the Gram-Schmidt process. So what this method is about is creating orthogonal bases. So what does this even mean when we speak about an orthogonal basis? If we think about our traditional usual xy plane, and we have two vectors that represent this, for example, 1 0 and 0 1, we just saw now in the last example that these two are orthogonal. And what this means is that any kind of vector that is represented in the xy plane can be written as a combination of these two vectors 1 0 and 0 1. So these two vectors are said to form an orthogonal basis because they are the basic directions by which we can represent any vectors in this plane. So if we look at another example, and that's one that's commonly seen in physics, that of an inclined plane with an object on the top, as you can see in this diagram. So you would know that if we have two vectors, let's just draw two vectors. So we have v1. So this is like an applied force that is parallel to the inclined plane. And then we have another vector, perhaps v2, that's acting like that. So when we analyze this system, we would traditionally put v2 into two components, a parallel component and a vertical component. And we would also maybe show, for instance, the force of gravity acting downward. And then we would also have the normal force acting perpendicular to the plane itself. And then we would write all of the different components in terms of the different directions. So what is traditionally done is that we would regard two set of axes. And the one axis is the y-axis, and we would regard that as perpendicular to the slope. And we would have another set of axes, the x-axis, and that's taken as parallel to the slope. So this is what we mean by when we say we're creating an orthogonal basis. So when we create an orthogonal basis, we are creating these two axes. So we'll call it u1 and u2. So we'll say u1 is this vector that points along this slope. It's parallel to the slope, and it represents the movement of this object moving up the slope or even down the slope, but we'll say up the slope because of this vector, this force vector v1 that is acting up the slope. Then also we have one other vector u2. So u2 is perpendicular to u1, and that represents the normal force that would be acting on this block, and it would also represent the perpendicular component of this force vector v2 that is acting, and it will also represent the perpendicular force of gravity. So gravity would act downward, and it would have two components in the direction of u1 and u2. So how do we create u1 and u2? When we say that, we're asking what are the components of u1 and u2 relative to our traditional xy plane. So u2, what is the x and y values of u2, and also the x and y values of u1. So the procedure that we follow to determine u1 and u2 is using this Gram-Schmidt process. And it's a stepwise procedure, and it's as follows. So firstly, we'll have two coordinate systems for v1 and v2. So we'll just say that v1 is equal to 3, 4, and we'll say that v2 is equal to 5, 1. So the Gram-Schmidt process would be described as finding u1 and u2 given v1 and v2. So step one is essentially to set u1 equal to v1. So this is the most obvious step. So it's the first and most obvious step because we can see that u1 is in the direction of v1. Therefore, we can easily see that we can create u1 as being our first vector in this entire step. So we're going to say that u1 is equal to 3, 4. Then the next step, step 2, is to project. We're going to project v2 on u1. So what we're going to do is that we're going to take v2 and we're going to split it into its two components. So v2 will have a component in the direction of v1. Let's write that in orange. So it will have a component like this. So this is the component of v2. So we're going to write that as the projection. It's going the projection of v2 onto u1. So this u1 is written as a subscript. And there's a formula for this. And this formula is given as v2 taken with the dot product of u1 divided by the dot product of u1 with itself times u1. So where does this formula come from? Well, it's not a difficult thing to see. We can take v2 and we can write it as the sum of its two components. So the first component is the projection along the direction of u1, as we had just shown. And also we'll have a perpendicular component. So initially we had v2, so v2 was something like that. And now we're saying that this is this component, and we have a perpendicular component. So we're going to multiply both sides of this equation by some kind of constant, a scalar constant. So that will be c. So we have cv2 is going to equal to c times this projection of v2 onto u1. So we'll show that as c times u1 plus the c times this perpendicular component. So the next thing that we're going to do is now we're going to multiply both sides of this equation. In other words, we're going to take a dot product of both sides of this equation with u1. So we're going to have c times v2 equal to c dot u1 with u1 plus c with this perpendicular component with the dot product of u1. So immediately we're going to see that this second term is going to equal to 0 because they are perpendicular. We have a perpendicular component being multiplied in the direction of u1. Remember that this is the direction of u1, so that's the direction of u1. And now if you have a perpendicular component multiplied by some vector in the direction of u1, it's just going to give us 0. So that is a known fact of vectors. So I just neglected just to write here u1. So all we need to do now is just solve for this constant c. So this constant c is equal to now v2 u1 divided by u1 u2. And remember that the projection of u1 onto v2 is given as c dot u1. That's what we have written it, because c dot u1 represents in the direction of u1 some scaled factor of it. It's some factor of u1 in this direction. So if we just multiply both sides of this equation, c dot u1, so c u1 is the projection of u1 on v2, and this is how we get this equation, this relation, v2 u1 divided by dot product of u1 with itself times u1. So I just applied this formula so we can remember what v2 and u1 is equal to. So just remember that u1 was equal to v1, which is equal to 3, 4, and v2 was equal to 5 and 1. So v2 times u1, it's going to be 5 times 3, which is 15, 15 plus 5, which is, 15 plus 4, 4 times 1 is 4. So it's going to be 15 plus 4, which is 19. So I have 19 in this numerator. Then I have u1 dot u1. So u1 is going to be essentially 3 times 3 plus 4 times 4, which is going to give us 9 plus 16, which is 25. 25 times u1. So u1 remains as is. That's 3, 4. So I have 19 over 25 times 3, and then 19 over 25 times 4. And that's going to give me a vector. So I just put it in decimal form. So it will be 2.28 and 3.04. And then the final step of this Gram-Schmidt procedure is to determine u2. And how do I get u2? If I go all the way back up here, so this was the component of v2 in the direction of u1. So this was the projection of u1 v2. So the question is, what is this perpendicular component? Well, all it's going to be is it's going to be v2 minus this projection of u1 in the direction of v2 in the direction of u1. So that's a basic fact of vectors that people study in elementary study of vectors. That's easy to see. So it's going to be v2 minus the projection v2 in u1. So v2 was given as 5, 1. This is now subtracted from 2.28 and 3.04. So the coordinates of v2 are 2.72 and minus 2.04. So this is how we determine u1 and u2 as the orthogonal basis of this set of vectors v1 and v2, or rather given this set of vectors v1 and v2, such that we form this orthogonal set which allows us to write the components of vectors in these two directions and analyze it thereafter. So the final part of this video is about Hilbert spaces. So Hilbert spaces are an extension of what we've discussed already. So it's just a type of vector space, and it's very important It's fundamental to quantum mechanics. So it's a vector space just like the ones we've discussed, but it has some unique properties. And what these unique properties are is that it extends vector spaces to infinite dimensions. So whereas just now we've spoken about the inner product spaces and so on in 2 dimensions and 3 dimensions and so on, and all of these analysis took place in finite dimensions. However, Hilbert spaces are characteristic in that they have infinite dimensions. So what's characteristic about this is that all the previous analysis in terms of the inner products and so on still apply, but there's an additional criteria in that we have to have completeness. What completeness means is that we have any sequence of vectors, and this sequence of vectors will approach a limit. And this limit here must converge to a point within space. So this limit must converge to a point within that space. So if you think about in quantum mechanics, we have a particle or an electron or something like that, and we can think about its location or its position as a state. So that's what we would call a state. And all possibilities of this particular electron or whatever it is captured within the Hilbert space. So every possible position or location is inside the Hilbert space. And also we have to speak about orthogonality. So if we're speaking about states and if we speak about different vectors being orthogonal, then it means that we're talking about independent states. Remember that if we speak about the projection of one vector on another, and if they are orthogonal, it means that they have nothing in common. That's why their dot product is equal to 0. So that means that they are independent. So if we speak about states as location, it means that their positions are completely independent and they don't overlap in any way. So if it's in one location, then an independent position means that they're not overlapping. So in general, we can write a wave function as representing this kind of location. So we perhaps might use the notation psi. We can speak as psi of x as being the wave function or the probability amplitude of finding a certain particle or electron in one location. We can also have another location, perhaps phi of x. So just once more, these are possible wave functions that represent the probability amplitude. So this is the probability amplitude of finding a particle at a certain position x. So maybe along one direction, we have just this x direction here. So this is just in this one single direction. So if we take the dot product of this two, or the inner product, so the inner product corresponds in Dirac notation. It would be this psi of x and then we would be taking this dot product with phi. And this would equal to this psi of x times this phi of x. And then we'll be integrating this from minus infinity to positive infinity in the direction of x. So if this is equal to 0, then it's the same as the inner product. It means that these two functions are orthogonal. And what this means is that each of these wave functions represent specific distinct positions. And therefore, that's why their dot product will equal to 0. In other words, they wouldn't overlap. And then after that, if we actually measure its position, we perform a measurement, then we are collapsing this wave function to a specific point or region such that we would locate it in Hilbert space itself. So throughout the course of this video, we first started off with what the inner products were and inner product spaces, and then we spoke about orthogonality and then how we form an orthogonal basis using the Gram-Schmidt procedure, and then finally, it's worth mentioning that Hilbert spaces actually provide the entire mathematical foundation for quantum mechanics. What they do is they allow us to use vectors and inner products to calculate probabilities, distances, transitions, and it generally allows us to work within infinite dimensions in a well-defined way. So that gives us a framework to understand all of quantum phenomena, and while preserving the features of vector spaces like inner products, orthogonality, and so on, but just in a more abstract manner. So thank you very much for watching.